We can actually look back almost 13.8 billion years, which is very close to the Big Bang. But what if I told you that the end of the universe is no different from its beginning? The James Webb Telescope made an amazing discovery. The universe has stopped expanding. Popular scientist Brian Cox made this prediction years ago, giving us the most realistic starting point for imagining the end of the world. Now we can look at light that began its journey before galaxies, the oldest light in the universe. This is one piece of evidence for those who doubt the Big Bang. We are going to Big Bang 2.0. Join us as we explore why the world's expansion stopped because of James Webb's terrifying discovery. The Big Bang Theory is central to understanding the universe and its history. There are alternative theories about the beginning of the universe, such as eternal inflation or an oscillating universe, but today we will focus on the Big Bang, which is widely accepted in the astronomical community. The Big Bang is not just a theoretical astronomical word. It is the event that gave birth to our universe. But unless you're a space geek who spent hours looking at renderings of the Big Bang, you might not know the intricate details. The original explosion started from a single point, an infinitely hot and dense point that blew for an extremely long time. This happened when the universe was only 10 to the power of negative 34 seconds old, an incredibly brief moment when the universe underwent an explosive, faster-than-light burst of expansion. In a second, the universe was filled with all the particles we had learned about: protons, neutrons, electrons, anti-electrons, photons, and neutrinos. Our understanding of the origin of the universe is very theoretical. We've come a long way since the first moon landing, and technological advances have exploded. If scientists relied only on mathematical formulas and models, they could never imagine exploring the possibility of life on Mars. The cosmic microwave background is our best piece of evidence, allowing scientists to observe the echo of the Big Bang. However, this method has limitations. We do not see gravitational waves or residual radiation from the expansion itself. Despite these limitations, our knowledge of the Big Bang is still solid. According to the theory, our universe is still expanding. For decades, the Hubble Space Telescope was our primary tool for studying the Big Bang, and now we have the James Webb Space Telescope. But here's the catch. The James Webb Space Telescope tells us that the universe has stopped expanding. While the world is still intact, you may want to improve your online experience. Sponsored by Atlas VPN, with over 6 million users worldwide, they offer a secure and accessible online experience for just $1.83 per month plus 3 additional months. Atlas VPN keeps your browsing secure and unblocks content from around the world. Get everything with one subscription for all your devices. Click the link in the description to take advantage of the limited time. Let's delve into the origin of the universe. The Big Bang Theory claims that everything we know, space, time, matter, and energy, originated from a single, infinitely dense and hot place. The concept of a singularity challenges our understanding of physics because it is the point where our current laws of physics break down. This period of rapid inflation created a vast, expanding universe full of particles. The Big Bang Theory is not just a random idea. This is supported by several lines of evidence. One of the strongest clues is the cosmic microwave background, CMB. Discovered by Arno Penzias and Robert Wilson in 1965, a faint glow permeates the universe and is a remnant of the Big Bang. The CMB provides a snapshot of the universe when it was only 380,000 years old, revealing its early structure and composition. Another proof is the abundance of light elements such as hydrogen, helium, and lithium. These elements formed in the first minutes of the universe in a process known as Big Bang nucleosynthesis. The observed proportions of these elements in the universe are consistent with the predictions of the Big Bang Theory. Scientists believed for decades that the universe had been expanding since the Big Bang. This idea was first proposed by Belgian astronomer Georges Lemaitre in the 1920s and later confirmed by Edwin Hubble's observations of distant galaxies. Hubble discovered that galaxies are moving away from us, and the farther away they are, the faster they are moving. This led to the formulation of Hubble's law, according to which the speed with which a galaxy recedes is proportional to its distance from us. The discovery of an expanding universe changes our understanding of cosmology. This suggested that the universe was once dense and extended over time. However, the nature of this expansion has been the subject of intense research and debate. In the 1990s, observations of distant supernovae revealed that the expansion of the universe is accelerating, driven by a mysterious force known as dark energy. Dark energy is one of the greatest mysteries of modern physics. It is thought to make up about 68% of the universe, with dark matter making up 27% and ordinary matter only 5%. Dark energy acts as a force that opposes gravity and causes the expansion of the universe to accelerate. However, the nature of dark energy is still unknown, and understanding it is one of the main goals of modern cosmology. The James Webb Space Telescope, JWST, is a game-changer in astronomy. Launched in December 2021, JWST is the most powerful space telescope ever built, designed to follow the Hubble Space Telescope. With a large main mirror and advanced instruments, JWST can observe the universe in unprecedented detail and capture light from the first galaxies that formed after the Big Bang. JWST operates primarily in the infrared part of the spectrum, which allows it to see through dust clouds and probes that are too dim or distant for Hubble. Its mission is to study the formation of stars and galaxies, the atmospheres of exoplanets, and the nature of dark matter and dark energy. JWST's observations could change our understanding of the universe. One of the most important discoveries of JWST is the revelation that the expansion of the universe has stopped. This finding challenges our current understanding of cosmology and suggests that we may need to revise our theories about the fate of the universe. If the universe is no longer expanding, it could mean that dark energy doesn't work the way we previously thought, or that there are other forces that we don't yet understand. The discovery that the universe has stopped expanding has profound implications for our understanding of the cosmos. If the expansion stopped, it could indicate a change in the balance of forces governing the universe. One possibility is that dark energy has changed its behavior or is slowly evaporating. Another possibility is that there are other, unknown forces at work that oppose expansion. A stationary universe would have significant implications for the ultimate fate of the cosmos. In an ever-expanding universe, galaxies move away from each other, and over time the universe expands. But in a static universe, the gravitational pull between galaxies can eventually cause a collapse, resulting in a big crunch scenario where the universe shrinks back to the singularity. This discovery also raises questions about the nature of time and space. If the universe stops expanding, it could mean that time itself is slowing down or even stopping. This idea is speculative, but it underscores the need to deepen our understanding of the fundamental nature of the universe. The idea that the universe could stop expanding or even collapse is not new. In fact, several alternative Big Bang theories have proposed such scenarios. One such theory is the Big Bounce, which suggests that the universe undergoes a cycle of expansion and contraction. According to this theory, the current phase of expansion could be followed by.
This theory was popular in the mid-20th century, but fell out of favor after the discovery of evidence supporting the CMB and the Big Bang. Recent observations from the James Webb Space Telescope may prompt scientists to consider these and other theories. It is possible that the true nature of the universe is more complex than we currently understand, and many theories may be necessary to explain its behavior. The discovery that the universe has stopped expanding is based on observations from the James Webb Space Telescope. Observational evidence is crucial in cosmology because it provides the necessary data to test and refine theories. However, interpreting this evidence is difficult because it often involves making assumptions and dealing with uncertainty. For example, measuring the expansion rate of the universe involves looking at distant galaxies and calculating their redshifts, which show how fast they are moving away from us. These measurements are affected by several factors, such as the motion of our own galaxy and the presence of intermediate matter. Therefore, scientists must carefully analyze the data and account for these factors to draw accurate conclusions. The James Webb Space Telescope's advanced capabilities allow it to make more precise measurements than ever before. However, interpreting these measurements requires sophisticated models and simulations. Scientists use these tools to understand the underlying processes and to test different hypotheses about the nature of the universe. The discovery that the universe has stopped expanding opens up new avenues for research in cosmology. Scientists will need to develop new models and theories to explain this finding and to understand its implications for the fate of the universe. This will require collaboration between theorists, observational astronomers, and experimental physicists. One area of research will focus on the nature of dark energy. If dark energy is not behaving as previously thought, scientists will need to investigate its properties and how it interacts with other forces in the universe. This could lead to new insights into the fundamental nature of the cosmos and the development of new theories of physics. Another area of research will explore the possibility of a static or contracting universe. Scientists will need to study the behavior of galaxies and large-scale structures to understand how they're affected by the lack of expansion. This could involve using simulations and models to predict the future evolution of the universe and to test different scenarios.